And he's going to be talking about high-resolution simulations of cold gas flows.
Okay, good morning. In this talk, I will present two different topics. The first one is which is a work in progress, and I am doing in the Hebrew University with Avishai Dekel. And the other one is part of the work I did in my last year in the PhD in collaboration with a group in Mexico, Pedro Colín, Vladimir Avila-Riz, and Octavio Valenzuela. Okay, for the first part of the talk, basically what we are trying to do is to make simulations of cold gas filaments in a high resolution in a cosmological context, following the work that Nirman Delker did and was talking in Monday. And basically how we want to do that is using the zoom-in cosmological simulations with the Ramses code, the most recent version, but for the moment without the black holes and the AGN, and then applying a different refinement criteria than the one that is usually used. Usually the refinement criteria that is used is based on density or mass. We want to apply another refinement criteria to focus the refinement and the high resolution on the filaments. Okay, well, basically the code, as I told you, is the Ramses code, the most recent version that Roman Tessier posted in the internet, and well, some of the main parameters that we are using are these ones here. And basically what we do is the usual zoom-in technique, that is to run first low-resolution dark matter-only simulation up to redshift 0. Then we select the system we are interested into making high resolution, and then we go back to the initial redshift and add baryons and higher resolution. Basically, we selected here a halo that is very massive. We want to get a system that has this very hot gas halo around it. With the filaments penetrating, with the cold filaments penetrating to it. And we also, to ensure that, we also want that at redshift 0 with the dark matter only, this system is just in the middle of the intersection of several dark matter filaments. The first high resolution simulation is using the usual refinement technique, and when we get a snapshot in where the cold flow is very evident through the hot gas halo, then we apply the new conditions for the refinement. Well, basically here is it's going very slow, and the resolution is not very good, but well, this is the high resolution simulation with the usual refinement technique up to redshift 2, and you can see, well, density, here temperature, and here entropy, and you will see that at around redshift 2, which is the last snapshot I put it here, you can see that it will appear a cold filament going inside the hot halo that is being generated here. You can see that there are these three filaments folding to the system, and here a cold filament that is going inside the hot halo. This is the model we are using for testing, and when we reach this point in where we have this cold filament penetrating the hot gas halo, what we do is to apply the new refinement criteria. The new refinement criteria basically is, first of all, we select geometrical limits, which is in this case 2 virial radius around the system. We want to have the high resolution inside this region. The second constraint we put is in density gradients just around the walls of the filament. But we also want to have high resolution inside the filament. Then what we do is to apply another condition, but now for the entropy, an entropy limit, what allows us to refine the central part of the filament. And to reduce the CPU time, we are not interested into having a high refinement in the central galactic system, and neither in the CGM in where the other conditions can be fulfilled. Then we apply a limit in the maximum density and in the limited density. And what we want to reach is a spatial resolution below these 10 parsecs, which is what will allow us to study the instabilities in the cold filament. Some very preliminary results for this testing case. In here I show you the AMR grid and the density. You can see that using the usual refinement criteria, we are refining only the central system. If we apply the new refinement criteria, we are not refining the central system in the highest resolution, although we are also having here a high degree of refinement because of the boundary conditions for the AMR. And we are also refining the filament quite good. Here are some other examples. You have the main system in the center and the filament that is well refined. And here another, well, this is supposed to be videos, but well. Okay, then the next steps is basically we want to reach this high resolution. For the moment, for testing, we allowed the code only to go to around 100 parsecs, but it's only for testing. Now we will make the new simulations having a higher resolution. We want to use more massive halos with clearer filaments and with another kind of systems to have statistics and different scenarios. And once this will be reached, we will start analyzing the filament following the work started by Pioneer. Okay, that was the first part of the talk. In the second part, I will present very fast these results from the analysis of Milky Way size galaxy simulations, in this case using the ART code, and Milky Way size models at redshift 0. And why we wanted this kind of models? Well, basically what we wanted was to generate kind of mock catalogs of the Milky Way to be prepared for the new data of Gaia and to compare the results we obtain in the simulations with the results of the real data. Basically, we again use zoom-in cosmological simulations, now as I told you, using the ART code. And the available simulations we have now are the Garrocha simulations presented in this paper in this year, and also the one of Colin 2016 is another set of models of Milky Way-sized galaxies. The first one, the Garrocha one, basically is a set of models with the same initial conditions, only changing feedback recipes, the spatial resolution, and also the refinement criteria. What we wanted here is to try to test the convergence, but also to find the best feedback and star formation recipes to obtain results that can be compared with observations for the Milky Way. Something that is maybe funny to find here is that we make hard thinking to try to obtain this acronym, and we found that it's completely possible to get all the acronyms you can imagine if you use the proper technique, like this one. And at the end of the talk, I will show you why we wanted to put Garrocha to these models. Okay. The second, well, for the Garrocha models, basically to tell you that we are obtaining a rotation curve that is that fits inside the observational limits. Here you have in this plot here the rate data for the star-forming regions. Also, the Chemin theoretical curve that is a curve that corrects for the non-circular motions of the data from software and collaborators, which is the red points here, and correcting the non-circular motions of the bulge, we obtain that the rotation curve of the Milky Way is not so peaked in the center. And if we put our model at the top, which is the solid line, we can see that we are fitting quite good the rotation curve for the Milky Way. Also for the stellar component, we obtain at the end at redshift 0 this very thin disk of young stellar population. You have here H, the youngest population, the oldest population, 3 different plots. And you can see also we obtain flares, and in some cases also we obtain warps, etc. And a lot of internal substructure. Here a detailed view of the stellar component. You can see a bar and very nice spiral arms, and also for the cold gas. Okay, the second set of simulations are the Colin and collaborators 2016. In this case, is using exactly the same prescriptions for the feedback and for the star formation, but now what we changed is the initial conditions. We selected different halo and halo masses at the beginning, and we resimulated them up to redshift 0. In all cases, also in the previous one, the initial conditions we selected are that in the dark matter only simulation, the halo falls in a not very populated wall, and also that has no major measures in the last giga years. Here are the morphology. You can see we have, from these 8 different models, we obtained 4 of them that are disk dominated and 4 of them that are bulge dominated. And the ones that are bulge dominated, 2 of them is due to a major measure in the recent years, and the other 2 we are still studying why we have these systems with a very prominent bulge. Here you can see basically this, the SP85. You can see here in the mass assembly history, we have this major measure here, And for the SP4, we have these three major measures that are making the system to be voltage dominated. Some other results, the rotation curves, all of them are non-peaked and quite flat. And also here you have the kinematical decomposition, and you can see that four of them, this one, this one, this one, and this one are disk-dominated, and the other ones are voltage-dominated. Several other tests that are fitting within the observations. We are obtaining quite good agreement with the stellar mass versus virial mass for all the models. You here have the curve presented by Rodriguez Puebla 2015, and we have all our models that are falling inside the range here marked as this gray region. Only to know that the Milky Way falls more or less like around in this region. Another comparison, also the star formation rate at redshift 0 is compatible with the one observed in the Milky Way for most of the cases, and lots of more tests and comparisons with the Milky Way can be found in these two papers. For example, we are also fitting the exponential profile of the Milky Way and several other parameters. Okay, a first analysis we could do using these models is the distribution of hot gas, and we wanted to do that because we can see that the hot gas is not isotropically distributed around the galaxy, and due to that can be a problem when we try to infer the total amount of hot gas in the Milky Way. Why? Because we can only observe the hot gas in the Milky Way in the directions in where we have quasars that their light can be absorbed by the hot gas when they are going to the observer. Then, for example, some works use only 8 directions in the sky to try to find the amount of total hot gas that is in around the Milky Way. Doing that, it can lead to a very important biases, and we tested that. In fact, you can obtain values that are from 2 times to 5 times more hot gas mass in the galaxy if we use the usual observational techniques. We made some mock observations of the column density of the hot gas, and again, as you can see, is very non-isotropic. And then, if you are not having a representative distribution of points, of observational points, you will obtain a very wrong result for the total hot gas mass. We also analyzed the origin of the hot gas in our systems, and this is one of the examples in where we can see this inflow of low metallic gas. You have here the metallicity, and the arrows are velocity. You can see that hot gas with low metallicity is infalling, in this case associated with the accretion of a satellite. We also have enhanced hot gas, which is basically a consequence of the stellar feedback from the inside of the galaxy, and we have some regions with recycling that you can see just in these regions of the system. Okay, then some work in progress that we have in mind, basically to make comparisons with the Gaia data, which is oncoming. In the next September, we will have the first release of Gaia in September 14th. And we will have the second release with a very detailed proper motions and very high precision, also parallaxes for stars in autumn 2017. We also are interested into analyzing the bulge formation of all our models, because we found that the bulges are multi-component. You can see, for example, here a plot of the stellar component as function of age. You can see that we have a young bulge component that is just in that direction, the semi-major axis, while the semi-major axis of the old component is just 90 degrees misaligned. We also saw that this has an origin, a secular origin from the disk. This has an origin from a major merger occurred at redshift around 2. And here I plotted the alpha enhancement versus the radius and the velocity. And you can see that for the bulge component, we have several different alpha enhancements, what shows us that it is a multi-component bulge. And finally, we also want to study the spiral arm kinematics in that simulation, something that has not been done yet in cosmological simulations, as the number of stars we usually have in the simulations is not very, very high. And, well, only the future work and conclusions. For the part of the refinement on filaments, we want to make new simulations of filaments in more massive halos and to test our new refinement criteria to see if we can obtain these high-resolution filament simulations and to get a higher resolution and start studying the instabilities in these filaments. For the Milky Way size simulations, basically, we succeeded on obtaining these Milky Way size galaxies at redshift 0, fitting several observational parameters. And we think that these models will be useful to understand and to study the new data that will come with Gaia and GES and other surveys. And well, as I promised, why the big interest of putting Garrocha to my simulations? Well, basically because it's the place in where I born. It's basically a small region at the north of Spain. Very, very beautiful region. You are all invited, not all at the same time, but invited to come and visit the region. And thank you.
Questions?
So when you're trying to compare with things like Gaia, resolution is clearly very important.
Mm-hmm.
Can you outline the resolution tests you've already done and what you plan to do?
Well, basically, the comparison with the Gaia is more, the comparisons we want to make is more related with the spiral arm structures and large scale structures. With that, we tested that basically in the resolution we have here in our models, which is 100 parsecs, the best resolution we have. Basically, we tested that we can ensure that we are able to trace the kinematics of the spiral structures. The problem we have here is that maybe we need more stars than the ones that we have. The stellar mass of our smallest components is of about 3 times 10 to the 4. Then, yeah, it can be critical.
The trouble is that the gas disk and the O-star disk is thinner than 100 parsecs.
Yeah,
so
yeah.
100 parsecs is not adequate resolution.
For the thin disk, that's completely true. Yeah, we need more resolution. We did several other simulations of isolated Milky Way sized galaxies, and in this case, yes, our resolution is about 4 parsecs, and in this case, we can study quite good the spiral structures and the thin disk. But yes, we need to improve more the resolution to be completely able to study this.
Okay, one more quick question as we switch over.
Very quick one. The filament stuff you're doing is super cool, and I was wondering where this target resolution of 10 parsecs come from, and whether it's physically motivated or sort of computationally expensive motivated.
In principle, it's physically motivated. It has to be less than 10 parsecs to be able to trace the instabilities, for example, the Kelvin holes. This, I think Nir is more aware about the resolution we need, but yes, it has to be physically motivated, the resolution we need.
Basically 100 cells over a kiloparsec, which is the minimum size of the streams that we expect. We need at least 100 cells over the minimum stream.
Yeah, I guess that was really the question. How big are the filaments? And that answers it. They're kiloparsec wide.
Mm-hmm.
That's right, yeah.
If we don't resolve them, means we don't know the answer.
Yeah.
Okay, we need to move on, so let's thank Santi one more time.